Today we will talk about the wave spectra. The actually wave spectra means it's a quantitative description of how wave energy is distributed across different frequencies in ocean environment. That means here you can see this is the frequency axis and this is the energy axis. So if you see from some particular frequencies, this concentrated around this, the energy is too high. This kind of, for this frequency, this is the energy, this frequency, this is the energy, like that. Different frequencies, we have the energy, how it is distributing it. This is the wave spectra. Based on the wave energy, how is it distributed across different frequencies is called wave spectra. Here you can see the fundamental spectra is a Newman spectrum that represents the wave characteristics based on the wind speed and the fully developed sea conditions. The Newman spectrum serves as a baseline model indicating relationship between wind speed and wave generation. If the wind is more, then wave heights also it's going to be more, because it's going to give the more energy to the water surface. So those water surface will create larger waves. Here you can see the Pearson-Moscow spectrum. Actually here Pearson-Moscow spectrum, this wind speed, that is also part of the spectrum, like wind speed taken at a height of 19.5 meters above the sea surface. This parameter significantly influences wave formation. The physical meaning of the spectrum is that this is for fully developed sea conditions. Here you see the dependence on wind speed. The stronger the winds, that will generate higher waves with more energy. And the exponential decay, you see the e power minus g by 2 by f squared. That exponential decay reflects that higher frequency, the waves carry less energy. This you can see from this fact. Here the frequencies are higher, but it carries less energy. That means like longer waves only carries lot of energy. These are the longer waves. So longer waves, it will carry lot of energy compared to the shorter waves. Shorter wave means like a frequency is less. Frequency here in this point of time, you see this here, this if more frequency, this will carry less energy. For higher frequency waves, the energy will be less. Now you can see the difference between PM spectra and JONSWAP spectra. This PM spectra is applicable for fully developed sea, and JONSWAP is applicable only for partially developed sea and limited fetch. And peak shape, if you see, this is the broader peak and this is a sharper peak due to the peak enhancement factor. And Pearson-Moscow spectrum, it depends on the wind speed, but in case of JONSWAP, it depends on wind speed and also fetch and wave duration. Fetch is how much distance, long distance over which the wind is blowing over the surface. So if the fetch is longer, then you will get a lot of energy, then it will create a longer waves. So that is fully developed sea, you will have the fetch, longer fetch, but in case of JONSWAP, it will be fetch limited. And main focus of PM spectra will be general wave energy distribution, but in case of JONSWAP, it will be specific energy concentration at the frequency, peak frequency. Here you can see the Pearson-Moscow spectrum is particularly useful for fully developed seas. Right? It assumes that a wave field has reached a steady state, which typically occurs when the wind has been blowing over a fetch for a sufficient duration. So here you can ask, what is the primary variable in Pearson-Moscow spectrum? Primary variable in Pearson-Moscow spectrum is primary variable is wind speed, which significantly influences the wave development. How does a JONSWAP spectrum differ from the Pearson-Moscow? JONSWAP spectrum includes parameter peak enhancement factor to account for conditions with limited fetch and sharper peaks. In what conditions Pearson PM spectra most accurate? It is most accurate for fully developed seas where wind has been consistent over a long fetch. Here you can see what role does fetch play in the wave development. Fetch is the distance over which the wind blows across the water. Longer fetch allows for the development of larger and more organized waves. That is nothing but the fully developed sea. Here SF is the spectral density that indicates distribution of wave energy across different frequencies. Higher values of SF at a specific frequencies mean more energy is concentrated there, representing the most common wave sizes in the sea. Here you can see wind speed. Wind speed reflects the driving force behind the wave generation. Actually, wind speed is the driving force behind the wave generation. Because of wind, only wave is getting generated. Stronger winds produce higher waves. And the PM model assumes that constant wind conditions, which allows wave field to reach a steady state. That means it's a fully developed sea. In that formula, there is an exponential decay that ensures that energy density drops significantly for higher frequencies. This mimics the natural observation that longer waves only tend to carry more energy, not the shorter waves. When we have these higher frequencies, these are the higher frequencies. Here, these are the higher frequencies. Here we have the less SF. SF is less energy density. So longer waves, these are the longer waves. Longer waves carry more energy. Frequency is less, that is the longer waves, because time period is more. For longer waves, the energy is more. For high frequencies, these carry less energy. These are the shorter waves. This is the natural phenomenon. To account for this only, there is a parameter called e power minus g by 2 pi. This exponential term, decay, this exponential decay ensures that energy density drops significantly for higher frequencies. These are the higher frequencies. Here it drops significantly.